Hi again, Pre-Calc classes. It's time for another online lesson on Chapter 6, more trigonometry, yay. And as we said, this Chapter 6 will be a pretty heavy emphasis on graphing, and we'll do a lot of neat things there. But the first couple of lessons introduce us to radians and how to work with those. Now you may recall that a radian is simply another unit of measure for angles. We're more familiar with degrees, but radians we'll be using quite a bit in this particular chapter with graphing especially, and also with some other applications as well. So you should have a feel for how big a radian is. Here's the official definition of a radian. 1 radian, and again it's an angle measure here, and it's going to be the same as this arc length here, which we'll talk about in a bit. This has to be the same as the radius. So when those two are the same, then the angle that's formed in the middle, called the central angle, is 1 radian. And 1 radian is about 60 degrees. It's a little bit less than that. So that gives you a little bit of a feel for how big a radian is. Now, if we look, this looks pretty similar to your circle chart. I don't think you have to write this down, but you should remember or know or be familiar with all of the radian measures on your circle chart. For instance, 30 degrees is the same as pi over 6 radians, and 210 degrees is 7 pi over 6 radians. Not that you necessarily have to memorize those. You'll be able to use your circle chart, but you should become familiar with them so you don't always have to refer to your circle chart or stare at it to figure out some common radian measures. So just as last chapter we did things like the cosine of 60 degrees, you should also be able to find the cosine of pi over 3 or the sine of 5 pi over 4 because it's the same measures just in a different unit. The main thing we're going to be doing in radians in this lesson anyway is converting them to degrees and back and forth. And we'll show you in class a nice way to do it on your calculator. But here is an exact way of changing from degrees to radians and vice versa. So our first example here is to change 115 degrees to radians in terms of pi. Now whenever you see that in terms of pi, that means it should be an exact answer. So really we're going to start with our 115 degrees. I'll write that down. And then what I want to do is do a little conversion. I'd like to be able to cancel out degrees. And so I know from that first slide here, and this is something that you should become very familiar with, that in 180 degrees there are pi radians. So when I multiply this 115 degrees by pi over 180, the degrees will cancel out and I'll get an answer that has pi in its expression. So when I do this, I get 115 pi over 180. And I can ultimately reduce that fraction. You may need your calculator to do this. I can ultimately reduce that fraction to 23 over 36. The pi still needs to be in there. So that's an exact representation of 115 degrees in terms of pi, and that is in radians. So this ratio here is really crucial. We'll use that an awful lot. Alright, the next example here then talks about changing from radians to degrees. And again, this is probably a little bit easier because whenever you see pi radians, you can automatically substitute in 180 degrees. So I just do that in this case and multiply it out. Kind of forget about the negative sign maybe to begin with, just tack that on at the very end, and you get 157.5 degrees. But again, the whole notion here is this ratio. Very important in this first example and really very important in the second one as well. Next are a couple of things that seem a little unrelated, but definitely have to do with radians here. We're going to talk about a couple of famous mathematical formulas, arc length and the area of a sector. So arc length is kind of a fraction or a portion of the circumference. The circumference is all the way around a circle. So the arc length, usually designated by the letter S for some reason, is just this portion. And the portion that's cut off when we have this central angle and then a radius emanating to the edge of the circle. So that's the arc length. And the easiest formula ever that you'll ever see in pre-calculus is this one here. The way to figure out that arc length is to simply take the radius times that central angle. Now the key thing though is the central angle must be in radians, as you might expect. Now we can probably figure this out without the use of any of that formula. Let's just say that we have our circle that has 60 degrees. So my central angle here is going to be 60, and the radius is going to be 6 centimeters. Now, if I figure out the total circumference of this circle, again, I'm going to try to do this from my past knowledge here. You might recall that circumference equals 2 pi r. And if you can't remember that, I would ask you to hearken back to the familiar Twinkle, Twinkle, Little Star rhyme. Twinkle, twinkle, little star, circumference equals 2 pi r. So if you remember that, that helps you find the circumference. And then I just fill in some information that I know here. Here's 2 pi. I know my radius is 6. And so my whole radius is going to be 12 pi. What portion of that do I have? Well, 60 degrees is 1/6 of the circle. So if I just divide that by 6, I would get an answer of 2 pi for that arc length. Now, just to contrast that, let's actually look at the formula, which is this S equals r theta. I'm going to use that. So r is 6, of course. Now theta, watch out for that because it has to be in radians. So I can't use just 60 degrees. And if you look at your circle chart, you see that 60 degrees is pi over 3 radians. And sure enough, when I multiply this out, I'll get 6 pi over 3, which is 2 pi for the arc length there. 2 pi centimeters is what that would be. So you don't always have to use this formula. You can hearken back to some previous knowledge, but this is a pretty easy, direct formula that I encourage you to try. Here is another geometric term per se, the sector. And the sector of a circle is a slice or a piece of pie of the circle here. We're going to try to find the area of it. Here's the fancy schmancy formula that we can use. Once again, this theta has to be in radians. But let's see if we can find the area of our previous one we did before that has the central angle of 60 and r equals 6. Again, let's just use our previous knowledge here a bit and think about the area of a circle. And you probably remember that area equals pi r squared. If you can't remember that, think back to another little nursery rhyme, Fuzzy Wuzzy was a bear. Area equals pi r squared. So that's a way to help you remember that. So the area of that whole circle would be pi times the radius, which is 6 squared. That's going to be 36 pi. Once again, what portion of the circle is that particular area? Well, it's 1/6 of it. So if I divide by 6, again, I'm going to get 6 pi square centimeters. Now let's go to our actual formula and see if we can verify it with that. According to my actual formula, the area is going to be 1/2 times r squared. Well, my r squared is going to be 6 again, so 6 squared times that theta. Again, it has to be in radians, not degrees. So 60 degrees is that pi over 3. And we'll see if we actually multiply this out. This is 1/2 times 36 times pi over 3. I'm going to still get that same answer once again, 6 pi square centimeters. So the formulas work nice. Don't always have to have them. So that's our first lesson here, converting from radians to degrees and vice versa, and looking at a couple of familiar terms, the arc length and the area of a sector, using some radian stuff to help us solve them. All right, thanks for listening, everybody, and we'll see you guys in class.